theory had great explanatory power, scientists were still reluctant to accept atoms as real phenomena rather than philosophical abstractions. To quote science writer Brian Clegg, "As late as the early 20th century, there was still doubt as to whether atoms really existed. In the early days of atomic theory, atoms were considered by most to be useful concepts that made it possible to predict the behavior of materials without there being any true individual particles. But the journey had only just begun. In Dalton's theory, the only difference between atoms of different elements lay in their mass. Hydrogen was the lightest known atom, while the heaviest of the naturally occurring elements known in the 19th century was uranium. It was the latter which proved to be the key that transformed atomic science from a neat theory into something of enormous practical importance. In the words of journalist Piers Bozzoni, uranium's more dramatic potentials emerged in 1896, when Becquerel discovered quite by accident that it gave off invisible rays capable of fogging photographic plates wrapped in light-proof black paper. What the French physicist Henri Becquerel had stumbled upon was the phenomenon of radioactivity. It meant that Dalton's atoms were no longer just an abstract way of describing chemical reactions. Under certain circumstances, they could produce energy in a form that was previously completely unknown. Becquerel's discovery at the very end of the 19th century triggered a revolution in atomic physics that went on to dominate the first 3 decades of the 20th century. The driving force behind much of this research was a New Zealand-born scientist named Ernest Rutherford. Less well known than his near contemporary Albert Einstein, who we will come to in due course, Rutherford's work was arguably just as important. Rutherford was a pioneer of modern science in more ways than one. At the start of his career, scientific research was largely in the hands of individuals and small teams. But Rutherford, particularly after he became director of Cambridge University's Cavendish Laboratory in 1919, led the trend away from this towards the larger multinational collaborative projects that we associate with big science today. Together with his co-workers, Rutherford unraveled the substructure of the atom and showed how it was responsible for the radiation that Becquerel had discovered. Rutherford's work also opened up the possibility of nuclear reactions, analogous to everyday chemical reactions but involving much higher energies. Rutherford pictured the atom as consisting of a dense, positively charged nucleus, that's where the word nuclear comes from, surrounded by smaller negatively charged electrons. He originally envisaged these orbiting around the nucleus like planets around the Sun, but that picture was modified by one of Rutherford's colleagues, the Danish physicist Niels Bohr. For consistency with quantum theory, Bohr showed the electrons must be confined to discrete energy shells. As to the nucleus itself, by 1920 Rutherford was convinced this was made up of smaller particles in the form of positively charged protons and uncharged neutrons. This picture was confirmed in 1932 when his student James Chadwick found experimental evidence for the neutron. In its final form, the Rutherford-Bohr model is still considered a good approximation to the true structure of the atom today. See Figure 1, included in the bonus material. A particular atomic nucleus can be described by just 2 figures: the number of protons and the number of neutrons it contains. The number of protons, which is equal to the number of surrounding electrons, is called the atomic number, while the total number of protons and neutrons together is called the atomic weight. The chemical properties of an element are determined by its electrons and so depend only on its atomic number. However, an element of given atomic number may have a varying number of neutrons, and hence varying atomic weight. Different